Hello and welcome to the screencast for Chem Activity 30A, Acids and Bases. What happens when hydrogen ions are transferred between species? If I take a look at where we are in the class schedule, this is Activity 30A. It is the last activity in Unit 4. We are more than halfway done with the class because we have Units 5, 6, and 7 to go. So we actually passed the halfway point when we were on Activity 27. How about that? More than halfway done. So acids and bases. Model 1, there are 4 reactions. Question 1 says, examine those reactions. What happens to the species that acts as an acid in the left column as it undergoes the reaction to become the conjugate base in this column? Pause the video and write a sentence. So here's a good answer. You could say the acid gives up a hydrogen ion. So I kind of was, I'm getting lazy here. I should have said the acid gives up a hydrogen ion as it undergoes the reaction to become the conjugate base, right? That would be a much better sentence. Clearly I'm getting a little tired after doing 6 of these in one day and on number 7. But the ion is important because if you just say it gives up a hydrogen, then what do you mean by that? Do you just mean an H? Because you notice that it ends up with a negative charge. So we do need to say a hydrogen ion because a hydrogen ion is an H+. So you could say it gives up an H+, or you could say it gives up a proton. Hydrogen ion, H+, and proton are all synonyms, so that would work. A proton is an H+. You get something that now has a negative charge. Question 2. What happens to the base as it undergoes the reaction to become the conjugate acid? Pause the video and write your sentence. Pause now. So did you say it gains a hydrogen ion, or it accepts a hydrogen ion, or picks up a hydrogen ion? Something like that. So if I go from water to H3O+, it's picked up an H+. If I go from H2PO4- to H3PO4, it's picked up an H+. So you're ready to answer question 3. Review your answers to questions 1 and 2 and complete the following sentences. So go ahead and complete both sentences. Pause now. Right, so here I'm just putting in what I already had decided on numbers 1 and 2. So in an acid-base reaction, or at least in these acid-base reactions that we're looking at, the acid gives up a hydrogen ion and the base accepts a hydrogen ion. Got it? Let's apply that to a new situation. So based on our definitions, label the acid and the base in the reaction below. Pause now. All right, is this how you have it? The HNO2 must be making this NO2-, so it lost an H+, so it's the acid. That leaves water as the base because it became H3O+, and that accepted an H+ or a hydrogen ion. Does that make sense? Good, all right. Number 5. An amphoteric substance is one that can act as either an acid or a base depending on the situation. Review the reactions in Model 1 and identify any amphoteric substances. So I'll page that back up so you can look while the video is paused. So pause the video and identify any amphoteric substances. What did you find? Looking for something that you find in both the acid column and the base column, the thing I find is water, yes? In reaction 1, water acts like a base. but in reaction 4, water acts like an acid. So I'm going to write water as something that is amphoteric. Number 6. Review reaction 1 in Model 1. What is the difference between an acid and its conjugate base? Pause the video and answer the question. Pause now. Okay, did you write a sentence? Here's my sentence. I wrote, the conjugate base has one fewer hydrogen ion, H+, than the acid. The same thing we've been saying. Another way of saying that is one fewer hydrogen, and the charge decreases by 1. So what's not okay is to say that the conjugate base is negatively charged, because it's not always. In reaction 3, it's not negatively charged. But what I said is true. It is 1, the charge has decreased by 1. So if I start with H3O+ and take away an H+, it becomes a 0 charge. That's decreased by 1. If I start with HCl and it becomes Cl-, it's also lost an H+, and the charge goes from 0 to -1, which is decreased by 1. Okay, same question, but for a base and a conjugate acid. So what is the difference between a base and its conjugate acid? Pause and write a sentence. Pause now. You're getting this, right? I said the conjugate acid has one more hydrogen ion than the base. So this conjugate acid, H3O+, has one more hydrogen ion than H2O, so it has one more hydrogen plus the charge goes up by 1. In the case of HCO3-, the bicarbonate ion, we get to H2CO3. It has also gained an H and a plus, so the plus takes the charge from a negative to a 0. The charge increased by 1. If you want to write the charge increases by 1, go ahead and write that. And let's go on with Model 2. Conjugate acid-base pairs. So this kind of acid-base reaction that we have been investigating, these are called the Bronsted-Lowry acid and base reactions. These are it's a little bit more sophisticated than when we learned about acids and bases earlier and just said that an acid completely dissociates in solution to give you an H+ and an anion. This is a little bit more sophisticated way of thinking about acids and bases. And here's the sentence. A reaction of an acid and a base involves a proton, that is a hydrogen ion, transfer from the acid to the base. Two ions or molecules that differ only by that one hydrogen ion make up a conjugate acid-base pair. 3 example pairs are shown below. And then you have an example reaction. So look at that example reaction. And we'll go on with question 8. So this is the example, but now we're looking at reaction 2 in Model 1. Part A, what is the conjugate base of HCl? Pause the video and write your answer. Pause now. So did you get Cl-? I can actually do that without even looking at reaction 2 if I follow the definition, because if HCl was the acid, to get to the conjugate base, I take away the H+, and I'm left with Cl-. When I look at the reaction, there's my acid, there's my conjugate base, one H+ less than this, so Cl-. Part B, what is the conjugate acid of NH3? Pause now. Again, I could do this without looking. If I want the conjugate acid of NH3, that means this must be the base. So to get to the acid, I need to have one more hydrogen ion, so add an H and add a plus. If I go back and look at that reaction, NH3 was the base, NH4 plus is the conjugate acid, one more hydrogen and one more positive charge. Part C. Following the example in Model 2, draw lines onto reaction 2 in Model 1 to connect the conjugate acid-base pairs. So I'll page up to there. For reaction 2, pause the video and draw the lines. Pause now. Great, so HCl and Cl- are a conjugate acid-base pair, and NH3 and NH4 plus are a conjugate acid and base pair. These differ only by that one hydrogen ion. Got it? So let's apply that to some new situations. So here are some acid and base reactions. So go ahead for letter A, label the acid, label the base, label the conjugate acid and conjugate base, and then draw lines to connect the conjugate acid-base pairs. So do A first. Pause now. Okay, so the acid is the molecule that's given up the H+, and the conjugate base, I've abbreviated CB. Then we have, if this is the acid, this must be the base, and it picks up the hydrogen ion to give me water, which must be the conjugate acid. So this is another conjugate acid and base pair, water and OH-. Is that what you got? Gaining some confidence, I hope. And you're ready to do B. Pause and answer B now. So I'm not putting them in the same order, but you're still able to figure this out, right? F- and HF are a conjugate acid and base pair, which differ only by the H+. The F- must be the base because it picks up an H+. The H3O+ must be an acid because it gives up an H+ to become water, and there's my second conjugate acid-base pair. Pause if you need to, make any corrections, try to understand conjugate acid-base pairs, and we're ready to move on with Model 3. Strong and weak acids. So here's the statement. When a generic acid, symbolized HA, is added to water, the following reaction results. And there's the reaction. Here's how I will read it. HA plus water reacts to form A- plus hydronium. And the diagrams below represent the relative amounts of chemical species present in the solutions of two hypothetical acids at equal concentration. Water molecules are so numerous that they are not shown in the diagrams, but the fact that it's dissolved in water is indicated by the shaded region. And then notice there is a key over here. Pause the video now, examine the model, and answer question 10. Pause now. Okay, so I'm using the key. I know there's water, but I'm not writing water. But I notice this symbol, which appears to be H3O+ ions, so I wrote that down. And I see A- ions, so I wrote that down. That's all I see. Do you see anything else? All right. Same thing, but for question 11. We're looking at acid 2. Pause and write your answer. Pause now. Okay. List the species. I see this one, which is H3O+ or hydronium. I see this one. That's different. That's HA. And then I see this one, which indicates A-. All right. So number 12. A strong acid, and this kind of matches our definition from earlier when we memorized a list of strong acids. A strong acid is one that is essentially 100% dissociated in water, meaning it reacts completely with water and the reaction goes 100% to the products. In other words, this reaction goes completely to the products, reacting completely with water and giving you only the products. That's a strong acid. Which acid, 1 or 2, is a strong acid? And explain. Pause now. So did you say acid 1? Why is it acid 1? Because I'm looking at something that's gone 100% to the products, meaning there won't be any HA left. All of the HA will have reacted with water to give me A- and hydronium, and that's what I see in acid 1. There's no HA left. So that must be the strong acid. If I look at the weak acid, there is some hydronium and there's some A-, but there's still a lot of HA left over. That's because it's a weak acid, and many of those do not dissociate in water, do not react with water to produce hydronium ions. So there's a picture that helps you put a handle on the difference between a strong and a weak acid. This model 4 is the same list of strong acids and bases that we saw in an earlier activity. I believe that was activity 14. And now we're on activity 30A, but it's still the same list. And here's a statement. When weak acids and bases dissolve in water, they dissociate only slightly into ions. So let's move on with critical thinking question number 13. Write the 3 chemical species that actually exist in significant amounts in a 1/10 molar aqueous solution of HCl. And feel free to go back and look at the previous section to help you answer this. Pause now. HCl is on our list of strong acids. If I go back and look at this model, if it's a strong acid, it's completely reacted so that none of this is left. So the 3 things that are left are water, hydronium, and the conjugate base. In this case, the conjugate base is chloride. So hydronium, chloride, and the obvious but also easy to overlook one, and that's water. Number 14. Explain why hydrogen ion is not one of the 3 species that we just listed. So if you had listed H+, because way back in activity 14, I think it was 14. Yes, 14. We talked about dissociated into ions, and we actually even said acids give hydrogen ions and an anion. Well, we're being a little bit more sophisticated here. So work on your sophisticated answer and write an answer to number 14. Pause now. So here's my sentence. All the hydrogen ions transfer to water molecules to make hydronium. So that's a little bit more sophisticated. But when I look at this reaction, I can see that it's not just simply splitting up into H+ and A-, but what's actually happening, those hydrogen ions are being transferred to the water to make hydronium, and that's why we don't actually list H+. Now, if I'm doing math, it doesn't matter if I call it H+ or H3O+, because it's going to come out the same amount either way. Every single H+ that there is, if it attaches to water, becomes H3O+, and the numbers of them will be the same. If I have 100 H+, then I would have 100 hydroniums. If I have a mole of H+, I'd have a mole of hydroniums. The numbers will be the same. All right, so now let's do this for bases. Write the 3 species that actually exist in significant amounts in a 1/10 molar solution, aqueous solution of lithium hydroxide. Pause now. Did you get these? Now, lithium hydroxide is a strong base. It's also an ionic compound, and it actually does just split up into lithium ions and hydroxide ions. But then there's still water left over, the obvious but maybe not so obvious one. Okay, number 16. Write the 4 species that actually exist in significant amounts in a 1/10 molar aqueous solution of HCN. Pause and write your answer. Pause now. So in this case, there are 4 species. When we had the hydrochloric acid, we had hydronium and the conjugate base and water. Here we have hydronium, the conjugate base, and water. But we also have a large amount of the undissociated weak acid. That's a weak acid. I know it's a weak acid. First of all, it's listed as weak, and secondly, I remember that anything that's not in my list of strong acids is probably a weak acid. When I look at the picture is here, HCN would be analogous to acid 2, and since it's a weak acid, HCN, this dot would have to be the CN altogether, and the little tiny dot, the H, and so most of the HCNs remain stuck together. Only a few of them dissociate into hydronium and cyanide ions. How are you feeling about it? Are you getting a good feeling for strong and weak acids in the Bronsted-Lowry theory? Why don't you write a summary of the differences between a strong and a weak acid? Pause now. Okay, so I've summarized the differences as follows. For a strong acid, it dissociates completely. In other words, no HA remains. For a weak acid, it dissociates slightly. In this case, most of what is remaining is HA, and only a slight amount of it has dissociated. This question didn't ask me to say what is similar. Of course, they both produce hydronium ion. They both produce a conjugate base. It's just the extent to which they do that that determines what is a strong or a weak acid. Oh my goodness, can you believe it? We are to the end of this activity, which means we are to the end of Unit 4. Acids and bases are over. So you're ready to do the exercises. You can check the answers to the exercises in the exercise solution category on Blackboard. You can do the sampling homework to practice, and you are ready, once you've done that, to take quiz number 4. Cheers!